Welcome back to my video. So in my previous video I talked about basics of circuit theory and basic components, that is active component and passive component, right? So voltage we can also call it as potential difference, EMF, electromotive force. It is the energy required to move a unit charge through an element. And current, it is nothing but a flow of charge. Told you about DC and AC current. DC is a direct current, it remains constant, the value remains constant, and AC is the alternating current. It changes its polarity and magnitude with respect to the time. And coming to this basic components, we have active components, passive components. Active components supplies energy to an electric circuit. It can control the flow of charge, but passive components can only receive energy. It can either dissipate or absorb, right? So active components, we have example for this active component is, I told you, voltage sources, current sources, generator, transistor, diodes. An example for passive components are resistors, inductors, capacitors, and also transformers. Transformers used to step up or down the power voltage. The power and the energy remain same. Okay, so transformer is a passive device, passive component. So in my video, today's video, we are going to see the series parallel connection of the passive components. So circuits can be grouped into three, that is series connection, parallel connection, and series parallel. Combination of series parallel. So first let's take series. So the manner of connecting components end to end is called series connection, series circuit. So for example, R1 is connected, other end is connected to R2 and R3, etc. up to Rn. So this is called series connection, series circuit. So here same current circulates through every resistor. So current, let's take the current as I. So this current I flows through every resistor. So according to Ohm's law, so as per Ohm's law, the voltage across each resistor is the product of, so the voltage across each, that is voltage drop, the voltage across each resistor is the product of I into R. In our previous video, we have seen the relation of voltage, current and resistance, right? So based on the relation, your voltage across each resistor is I into R, right? So in series circuit, as the current remains same, so as I is same for all the resistor, your voltage drop, you can write it as voltage drop is proportional to the product of IR. As I is same, we can write it as your voltage drop across the resistor is proportional to the resistance value. Okay, so here as it is directly proportional, the R equivalent for resistors connected in series is the arithmetic sum of individual resistances. That is R equivalent is equal to R1 plus R2 plus R3 up to Rn. So here there are 3 points to be noted. First point is same current flows through all component. I is same for all resistors. Next, applied voltage is equal to let us say Vs. Applied voltage is equal to sum of the voltage drop across each resistance. Let's take this as Vd1, Vd2, Vd3, etc. up to Vdn. Okay, so the applied voltage is the sum of total voltage drop across each element. Vd1 plus Vd2, etc. up to Vdn. And the third point here to be noted is your voltage drop across individual component is directly proportional to your R. So in series resistance, the voltage drop is directly proportional to your resistance value. Next comes your parallel circuits. So here one end to one, the resistor, if the component one end is connected to one common point and the other end is connected to other common point. So this is a common point. If we have number of resistors, so this is connected to the common point. Another end is also connected to common point, and this is again connected to the negative terminal. This is positive terminal. Here the component will have, as they are connected in parallel, every component will have the same voltage drop. The voltage drop across this point is equal to your supply voltage. In parallel connection, voltage drop across these 2 points is equal to your supply voltage. So the voltage drop across each resistance are same. Again, as per your Ohm's law, the voltage drop is equal to I into R. So I is proportional to V by R. As your voltage drop is same, as V is same, your I is proportional to 1 by R. So here the equivalent resistance is given by it is the arithmetic sum of reciprocal of individual resistance. So 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus up to 1 by Rn. Right? Here also there are some points to be noted. Right? The first point is voltage drop across each resistance is same. And the second point is the current through each component is inversely proportional to your resistance value. And the total current, third point is the total current is the sum of individual branch currents. Let us say this is a total current I. So your individual branch currents are I1, I2, I3, etc. Again, your R equivalent here is for parallel connection, your R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by R1. If there are 2 resistors only connected in parallel, we can use this formula. R equivalent is equal to R1 R2 divided by R1 plus R2. This is used only if we have two. A combination of both series and parallel. And these circuits can be solved by Ohm's law and the rules of your series parallel connections. So as far as now we have seen the series and parallel connection and equivalent resistance value, equivalent resistances. So for an inductor, the formula is same. L equivalent for series, it is L1 plus L2 plus L3, etc. up to Ln. And again your L equivalent for parallel is 1 by L equivalent is equal to 1 by L1 plus 1 by L2, etc. up to 1 by Ln. So when they are placed close together, there will be interacting magnetic field. For this reason, it is preferable to have a single component. Normally, if there are more inductors connected in series or parallel, they used to shield the inductor in order to prevent the interaction between the magnetic fields, right? Next, capacitance. Capacitor is just like your resistance, but just opposite. The equivalent resistance formula is like your resistor. It is just, I'll tell you, your capacitance is equal to permittivity. This permittivity is A by D. So your capacitance is proportional to your area of the plates. If this is a capacitor, this area is directly proportional to the area and inversely proportional to the distance between these two places, these two plates, right? Also have another formula, Q is equal to C is equal to Q by V, where Q is the charge and V is the supply voltage. So capacitor is just two plates electrically separated. Its basic function is to hold a whole bunch of electrons on these plates. So greater the value of capacitance, more electrons it can hold. If the size of the plates, right, if the size of the plates is increased, the capacitance goes up. There is more place for the electrons to hang out. If the distance between the plates is increased, if the distance between them is increased, your capacitance decreases. Why? Because if the distance increases, the electrical strength, electric field strength decreases. So if the distance between these two plates increases, this strength decreases, it means that your capacitance decreases. So basically if the distance is increased, distance அதிகமாச்சுனா field strength கம்மியாயிடும், electric field strength கம்மியாயிடும், so capacitance value கம்மியாயிடும். If the area of cross section, the plate oda area வந்து increase ஆச்சுனா, your capacitance also gets increased because there is more space for the electrons to hang out here. Here generate. So here for the capacitance C equivalent, if it is series circuit, it is just opposite to that of your resistor. For series, your capacitance C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 up to 1 by Cn. For parallel, the capacitance value is C equivalent is equal to C1 plus C2 plus C3. So by connecting capacitors in parallel, we can store more and more connection. Your capacitance value is, but if it is connected in series, your capacitance value is decreased. It will have a small capacitance value compared. If it is connected in parallel, you will have a larger capacitance value. This is about the series parallel connection of a capacitor. But what is the reason behind this? That is, the relation is just opposite to your resistor. Why this is like this? Let's see with the picture.
Okay, see here. Here we are seeing three capacitors in parallel. So we can assume this as, if we bring it close together, we can assume the plate area of the plate increases. எல்லாத்தையும் connect ஒன்னா சேர்த்து பார்த்தீங்கன்னா area increase ஆகுது. So earlier we have discussed this. If the area of the plate increases, your capacitance value increases. Okay, the next picture shows three capacitors connected in series. So this we can assume it as, again bring it closer. If we make it as a one capacitor, then the distance between the two plates becomes larger. Okay, again we have seen earlier that if the distance increases, the capacitance value decreases. So if capacitors are connected in series, your capacitance value decreases. If they are connected in parallel, your capacitance value increases.